Imagine you are an engineer embarking on a week faced with a mysterious metal. Its high strength-to-weight ratio, corrosion resistance, and biocompatibility seemingly woven from the very stuff of engineering dreams. Yet the dream quickly unravels. This metal scoffs at your tools, spurns your blueprints, and resists conformity. And this is just the beginning of your troubles. Welcome to a workday with titanium. Titanium's thermal properties pose the first major challenge. Unlike most metals, titanium exhibits poor thermal conductivity, which makes it uniquely challenging to work with during machining operations. Specifically, pure titanium has a thermal conductivity of 15 to 22 W per mK, while its alloys can have conductivity values as low as 5 to 6 W per mK. In stark contrast, materials like carbon steel typically feature thermal conductivities in the range of 30 to 54 W per mK. This poor thermal conductivity results in a scenario where the heat generated during machining is not adequately dissipated, but instead remains localized between the workpiece and the cutting tool. This localized heat can lead to premature tool wear, especially for tools made of steel, as these materials lose hardness and strength as their temperature rises. Adding to this issue is titanium's unusual thermal stability. Titanium doesn't lose its strength rapidly with increased temperatures, unlike most metals, which soften significantly under the influence of heat. Consequently, when a cutting tool works against heated titanium, it encounters a robust and resistant material. Yes, you guessed it right. This also results in accelerated tool wear and the subsequent need for frequent tool replacements, both of which contribute to increased operational costs. The physical toughness and ductility of titanium also present notable challenges in machining operations. Titanium requires substantial energy to fracture due to its plastic deformation characteristics. The machinability of titanium, therefore, often results in long, continuous swarf, which not only complicates the machining process, but may also lead to a strain-hardened, damaged surface on the workpiece. Further complicating matters, titanium's relatively low Young's modulus 110 GPa introduces difficulties in achieving precise machining tolerances. This low modulus value results in an elastic snapback effect once the tool's pressure is removed, akin to that observed in aluminum and its alloys, although less pronounced. Titanium's chemical reactivity adds another layer of complexity to its manipulation. It has a proclivity to absorb foreign atoms from its environment, especially when fresh surfaces are created during machining. This automatic diffusion can lead to hastened wear on the tool or its coating, negatively impacting the lifespan and efficiency of the machining equipment. Additionally, titanium instantaneously forms an oxide film upon exposure to oxygen, which makes processes such as forging more complex. Unless these operations are performed within an inert gas environment, like an argon chamber, the process necessitates extensive preparatory and preventative measures, which could increase operational costs significantly. The interaction of titanium with other metals, particularly steel, presents another intriguing challenge. Contact between titanium and steel can lead to contamination, leading to what is often referred to as galling. The adhesion between sliding surfaces is what causes galling, a type of wear. This friction-induced adhesion can cause a transfer of material from the steel tool to the titanium part, which can degrade the surface quality of the titanium. The machining of titanium introduces significant safety risks due to the highly flammable nature of titanium swarf. When ignited, titanium swarf results in a Class D fire. We can say D for diva, characterized by extreme temperatures and resistance to traditional extinguishing methods. Titanium burns fiercely under standard atmospheric conditions and reacts vigorously with substances like water, steam, carbon dioxide, or nitrogen, exacerbating the fire instead of quelling it. Therefore, specialized Class D fire extinguishers and rigorous safety protocols are indispensable, although they can contribute to higher operational costs. Despite the associated challenges, careful management of these risks is vital for the safe machining of titanium. Despite the many challenges that titanium presents, its unique properties make it an indispensable material in high-performance applications. This seemingly stubborn and high-maintenance metal demands special attention, specialized equipment, and rigorous safety precautions, contributing to significant costs and time investments. However, the advantages titanium brings, superior strength-to-weight ratio, excellent corrosion resistance, and high-temperature resilience, outweigh these challenges in certain industries. The perfect example of this dichotomy is the massive Airbus A380, which employs approximately 70 tons of titanium in its structure and fittings. So next time you see an Airbus A380 soaring into the sky, remember that beneath its impressive exterior lies the handiwork of countless engineers who've danced with the metallic marvel known as titanium, their sleepless nights contributing to our safe and efficient air travel. This continued dance with titanium, as challenging as it may be, propels us forward in the realm of material engineering.